Hello everyone, I am Alex from WINDEO. In our previous video, we introduced the OTS-9000 point-to-point optical transmission solution. The video received great attention from many industry professionals. Today, I will provide a detailed physical layer performance test of our OTS-9000. This test will verify its actual performance and key specifications. For today's test, we use a prism analyzer and an Omnitech 4K toolbox. Why do we use different test instruments? Because different products and test instruments have different algorithms, interfaces, chipsets, and circuit designs. To accurately evaluate the true performance of our products, we have invested in various professional test instruments from different brands. The goal is to fully verify the performance and reliability of our products. Since the prism signal generator provides limited test patterns, we use the Omnitech 4K toolbox for additional testing. It can generate various test patterns, including pathological patterns. Therefore, we will use both instruments for today's evaluation. First, let's power on the device. As you can see, this is the DC power input interface. It features a secure locking design to prevent accidental disconnection. Its design is similar to our LEMO connector. The connector can only be removed by holding the release mechanism, ensuring a reliable connection. The device is also equipped with a Type-C power interface. If AC to 120 volts power is not available on site, a power bank can be connected through the Type-C port to power the device. Thanks to its low power design, a portable power bank can support the entire live production. Today, we use a 20-kilometer pure fiber link for testing. As you can see, this is a 20-kilometer optical fiber cable. Why do we use a 20-kilometer fiber instead of an optical attenuator? Because an attenuator cannot fully represent the actual transmission performance of a device. Why is that? Because optical signals experience dispersion during fiber transmission. Dispersion can affect the receiver sensitivity of the device. If we only test with an attenuator, it cannot accurately reflect the actual transmission performance. Therefore, to verify the reliability of our product, we use a real 20-kilometer fiber link for this test. Currently, both devices are set as transmitters. We configure one unit as the transmitter, and the other unit as the receiver. Double-click the screen to switch the transmitter into receiver mode. Now the device displays the real-time optical power. As the receiver, the current optical power is shown as -7 dBm. After transmission through a 20-kilometer fiber link, the optical output power is approximately 1 dBm. The receiver sensitivity is -7 dBm. This means the total link loss is approximately 7 dBm. This is consistent with the expected attenuation of a 20-kilometer fiber link. Now we connect the test signal. This cable carries the signal output from the Omnitech, and it is connected to our transmitter. As you can see, after the signal is connected, the indicator changes from red to green. It also displays 12G-SDI, lock, input, and loop status. This is the SDI loop through output port. At the same time, the loss counter increased by 1. This is because I disconnected the signal once. If we disconnect and reconnect again, the counter increases to 2. This indicates the signal loss event counter. The receiver also locks the 12G-SDI signal successfully. The loss counter shows 2 because we interrupted the signal twice during the test. Now we connect the Omnitech 4K toolbox input signal to the receiver. Then we use Prism as a reference for comparison. This is a 3G signal test. Since our products support 12G-SDI, the performance results for 3G-SDI are naturally excellent. We will not focus on the 3G results in detail here. Next, we will focus on the 12G-SDI performance. Now we switch the signal source to 12G. The test signal format is 3840 multiplied to 160 at 60p. First, let's check the signal lock status. As you can see, the device has successfully locked the 12G-SDI signal. The receiver unit also locks the 12G-SDI signal successfully. We are currently transmitting a 4K 60p signal. The Prism analyzer has also successfully locked the 4K 60p signal. Now let's check the eye diagram from Omnitech. This is our eye diagram measurement result. This is the reference eye diagram measured by Prism. Today, we will introduce the SMPTE to 082-1 standard. First, let's look at the eye diagram. As you can see, the larger the eye opening, the better the signal quality and overall signal integrity. According to the SMPTE to 082-1 standard, the rise and fall time must not exceed 45 picoseconds. Our measured result is approximately 35 picoseconds. The rise or fall time difference must not exceed 18 picoseconds. Overshoot and undershoot must not exceed 10%. The signal amplitude standard is 800 mV with a tolerance of plus or minus 10%. This means 720 mV to 880 mV are within the acceptable range. As you can see, our overshoot and undershoot are below 10%. The current measurement is around 8%, which is relatively high. Now let's look at the Prism measurement. The overshoot and undershoot measured by Prism are below 1%. This is why we use different test instruments to verify product performance. A single test instrument cannot fully represent the complete signal condition, because different devices and test instruments are designed with different principles. Their testing algorithms and analysis methods are also different. Therefore, we have invested in multiple professional test instruments. This includes the Leader 5600, which provides higher precision measurements. Today, by using both Prism and Omnitech, we can clearly observe the differences between different measurement platforms. By analyzing these differences, we can identify potential issues during product development. Now we will perform a pathological pattern test. We use Omnitech to generate the pathological pattern signal. As you can see, the device is correctly transmitting the pathological pattern. According to the eye diagram quality and measurement parameters, the results remain highly consistent. This is because our product circuit design, together with the optical module output consistency, is highly optimized. However, you can see that Prism shows a red alarm. Why does this happen? This is caused by a limitation in the Prism firmware. When testing pathological patterns, Prism cannot properly identify and analyze the signal. Although it can detect and display the signal, it shows a red warning during physical layer analysis. Therefore, we use Omnitech and Leader 5600 for further verification. The Leader 5600 can accurately measure pathological pattern signals, while Prism cannot perform this measurement correctly. The test results show that, after 20 kilometers of fiber transmission, our pathological pattern performance remains excellent. There are no CRC errors during the entire test. The CRC value remains at 0. This demonstrates the excellent transmission robustness of our product. Why is pathological pattern testing so important? Because SDI signals are different from conventional communication signals. SDI uses a specific scrambling process, together with non-return to zero inverted encoding, combined with its unique signal structure. YCBCR data can generate long sequences of consecutive zeros or ones. For optical modules, long runs of zeros and ones create significant challenges. For example, transmitting 30, 40, or even 80 consecutive zeros. For an optical module, this is equivalent to having no optical output, while transmitting 80 consecutive ones represents continuous optical output from the module. However, for SDI signals, these consecutive zeros and ones are transformed into a serial stream through the scrambling polynomial. During the descrambling process at the receiver, data recovery errors may occur, expected zeros may disappear, and expected ones may be incorrectly filtered. This can eventually cause signal interruptions during real-world transmission. Therefore, all of our products use WINDEO self-developed optical modules. Our optical modules can reliably pass pathological pattern testing over 20 kilometers. As you can see, I slightly moved the fiber cable just now. The current real-time optical power is -9 dBm. We can further increase the optical loss. Now, slightly disconnect the fiber further. The optical power has now dropped to -12 dBm. Even at a receiving optical power level of -12 dBm, the device can still correctly receive the signal. The signal was briefly interrupted when the fiber was moved. Now we clear the CRC counter. As you can see, the device continues to transmit the pathological pattern reliably. This demonstrates that our optical module and overall circuit design provide excellent transmission performance and stability. We have just cleared the CRC counter. As you can see, the device continues to transmit the pathological pattern signal stably. This proves that our optical module, both in terms of transmission performance and circuit design, delivers excellent quality and reliability. Our self-developed optical module is a unique solution in the market. You may have noticed that many optical transmission products on the market may experience flickering or unstable signals when additional attenuation is applied. However, our OTS-9000, even after 20 kilometers of fiber transmission, with additional optical loss applied, continues to maintain stable signal transmission. We have also tested the device at zero distance conditions, and the performance remains stable. This concludes the complete test of our OTS-9000. The prism analyzer was showing a red alarm earlier, so we will switch to another test pattern that does not trigger this alarm. Now we switch to a color bar test signal. The test images you see now are mainly static patterns. The dynamic test results are consistent with the static test results. So, this is today's complete test of the OTS-9000 product. In fact, this test method is not only applicable to OTS-9000, but also applies to all WINDEO SDI product series. The test signals, test methods, and implementation processes are consistent. Includes our optical modules and circuit designs. If you are interested in the OTS-9000, our technology, product quality, customized engineering services, please feel free to contact our team. Thanks for watching.